Hello, this video is meant to assist you with your understanding of the topics covered in Chapter 17 on waves. This is the basic definition of a wave. Aside from this basic definition, you need to understand that our book classifies waves in two ways. Things can either be a mechanical wave or an electromagnetic wave. The basic concepts we're going to cover here in this slide cover topics from Chapter 17.1 and 17.2. These basic ideas will carry us forth in Chapter 18. So it's very important that you understand the basics that I'm going to talk about here. We will save our examination of electromagnetic waves when we get to Chapter 18. But for right now, I want you to understand that a mechanical wave requires a medium. A medium could be any type of matter, solid, liquid, or gas, but we need a medium of some sort for a mechanical wave to exist. On the other hand, in Chapter 18, we're going to learn about electromagnetic waves. They don't require mediums. They can travel through empty space. Some examples of mediums may be the gas in the air. As you saw, for those of you that were in class when I did the Rubin tube demo, the gas inside the tube oscillated or vibrated at the frequency and the beats of your music. When I did the demonstration with the cordless drill and the string of the standing wave, you saw that the string was our medium. It was a solid piece of matter. And if you're ever out in the ocean waves require the water in order to have waves in the ocean. These are all examples of mechanical waves and the mediums in which they need in order to exist. When we examine mechanical waves, there are basically two types. The book we're using likes to talk about a third type. The first type is a transverse wave. It's the wave that oscillates up and down. We've all seen these waves. The longitudinal wave has vibrations that go in the same direction in which the wave is traveling. I want you to think of it as a slinky being compressed with little compressions. We'll talk about that more shortly. And lastly is a surface wave. As you can see right there, the definition, a wave traveling along a surface separating two mediums. All right, next slide. Looks like this. A transverse wave. This is our transverse wave. All right, some of the terminology you need to be familiar with this wave is the high points here. I'm going to try to highlight them here. These little high points here, all of them here, are called our crests. These down here are called our troughs, or troughs. The dotted line in the middle represents the rest position. Rest position, crest, and trough. These are some properties that we use for transverse waves. Next, we have a longitudinal wave. As you can see here, here's my slinky, and here's where my slinky compresses, area of compression, and here's where it expands. That's known as a rarefaction. Rarefaction. All right, all waves have the following properties. They have a wavelength, a frequency, a period, a speed, and an amplitude. And since they are moving at a regular interval, the technical name for that is called periodic motion. They oscillate up and down at a certain time in certain intervals. That's why it's called periodic motion. Every so often, the wave repeats itself over and over again. First thing we're going to talk about is wavelength. The wavelength is the distance between any two exact points of a repeating wave. If you look at the picture here, they're measuring the wavelength from crest to crest. You could also measure the wavelength from trough to trough. You need to be careful when you measure from this rest position, not just to go here because that would only be half a wavelength, but to go all the way over here to where the wave starts repeating itself. All right, the wavelength represents one complete cycle of the wave going up or down. If we were to look back at our longitudinal wave, it would be in between two similar points of compression or two similar points of rarefaction. Wavelength is measured in meters or any derived units such as kilometers, centimeters, millimeters, or any other type of unit for length. Period. Period refers to the time for one complete cycle to pass. Period is measured in units of time or seconds. In a few slides we're going to learn about frequency. Frequency is the opposite of period. The mathematical term for that is it's inversely related, which means that if we know the period, 1 divided by the frequency is equal to the period, or if we know the frequency, 1 divided by the period is equal to the frequency. We'll look at that more closely in a minute. Frequency. The number of times a certain wave cycles per second. The units of frequency are the hertz, abbreviated capital H, lowercase z. If you look at the graphic here, you will see different pictures of different waves. You can see that the red wave up here at the very top that I'm signaling here has a low frequency, while this purple wave down here has a very high frequency. It cycles lots of times, whereas the red wave doesn't cycle as quickly. So this has the waves up near the top, near the red, have a lower frequency, while the waves down here have a higher frequency. Wave frequency is related to the energy of a wave. The higher the frequency, the more energy a wave has. Amplitude. Amplitude is the distance from the rest position to the crest, or the distance from the rest position to down here at the trough, depending on where you measure. But these should be the same. This distance here from the rest position to the trough should be exactly the same as from here from the rest position to the crest. The assumption that needs to be made is that the wave is maintaining its energy and it's not losing any of its energy. Amplitude is a measure of a wave's energy. That's an important thing to remember. Amplitude. Amplitude, I believe, is also measured in units of length or meter. Next slide. Next slide talks about speed of a wave. This is important. We measure the speed of a wave by multiplying its wavelength times its frequency. The normal units of wave speed are meters per second. In Chapter 18, you will see that all electromagnetic waves theoretically travel at the speed of light. So, as the wavelength increases, the frequency would decrease, and the opposite would also happen. If the frequency increases, the wavelength decreases to maintain that constant. Here are some more wave facts. I mentioned the first one previously. Frequency of a wave increases, decreases the wavelength, and the opposite is also true. Increasing the wavelength decreases its frequency. You can tell a wave's energy by the size of its amplitude.